In progress.
Welcome to Unit 12. In this unit, basically, we'll build up on what happened in Unit 11, namely the fact that after Mr. Copernicus came up with the heliocentric model, basically, and explained among other things the retrograde motion of Mars. We were left with something that was really not good, and namely the fact that he believed that the path had to be circular. Of course, the interest grew, among other things, that the fact that the Earth is not the center of the solar system anymore. It's actually the sun is. And that created a problem around that time. So interest grew, and that's when Mr. Tycho Brahe came in with a lot of observations. Okay, let me share the screen first. So Mr. Tycho Brahe, who passed away in 1601, did a lot of observations, and of course he didn't have a telescope. He did all of them with basically visual observation with the data, and he had a mathematician by the name of Kepler. Mr. Kepler, basically, he didn't really have access to all of the data until Mr. Tycho Brahe passed away. At that time, he came up with 3 laws. The first law has to do with the path of the planets, and it's no longer a circle. Remember from your geometry class that the circle is all the points that are at the same distance from a center. Okay. Whereas an ellipse, which is the path of these planets, is no longer a circle, but rather an ellipse. So what is an ellipse? Is the collection of points that are at the same distance from 2 points, called the focal points. Okay, so it's representing a point of the ellipse. If I take the distance from the pencil to one of those tacks and add to it the distance to the other tack, that is the same distance from any point on that ellipse. So that is by definition what an ellipse is. Ellipse is characterized by several quantities. One of them is the major axis. If I take from focus to focus, from the focal point on each side, and extend that line all the way until I meet the path, which is in this case the ellipse. That distance from basically the furthest to that is the minor axis. So the major axis here is represented with the red line in here in the picture B, whereas the minor axis is with the green line, and here in this case is actually from the shortest distance on the ellipse. Okay, so the planet, like for example the Earth, at sometimes is very close from the sun, where the sun sits in one of the focal points. It doesn't matter which, any one of them will do. So in this case, the Earth is closer to the sun at some point, and it's further away from the sun in the opposite time. So when it's closer, it's actually during the winter solstice, and when it's further away, it's during the summer solstice. Then it's on the opposite sides in the spring equinox and the fall equinox, which is sitting right on the points where the 2 points are on the ends of the minor axis. Half of the minor axis is called the semi-minor axis. Usually we use the letter A for the entire for the semi-minor axis. The distance between the 2 focal points also is the characterization. Usually we use the letter C for it, or twice C in this case. Half of that is C. And that is distance, focal points, and the center of symmetry. And the distance between one of the points on the ellipse that are on the opposite, okay? For the case of the sun, the point that is closest to the sun is called the perihelion, close to the sun. And the further one is called the aphelion. So doesn't matter which one you take, as long as you go from that. That ratio is the eccentricity of the ellipse. In other words, how flattened is the smaller the b, then it's flattened, the eccentricity is high. Okay, when the eccentricity is zero, namely there is no difference, the two focal points will collapse on a single point and will produce a circle again. Okay, so in this case, in picture C, you have three different ellipses, if you wish. One of them is probably a circle in this case, because it's all the distances are the same. And that has an eccentricity of zero, and others have various values of eccentricities. Okay, so again, this is something has to do with geometry of ellipses. An ellipse is part of something called the conic shapes. Circle and ellipse are two special cases of that. There are other conic shapes. First law of Kepler says that basically the planet goes through an ellipse where the sun sits in one of the focal points. So it's no longer circular paths anymore. Okay. The second law of Kepler, if you take a line and you draw it from the sun that is sitting in one of the focal points to a planet and its path around the sun, it doesn't matter if it's Earth or any other planet, that line, of course, it's an imaginary line, that line sweeps equal areas in equal times. So for example, if it takes 2 months to go around this path, it takes 2 months to go through the other path. Obviously, the reason why they are is because the arc distance is small, but the radius is big. And the area depends on both the arc distance and the radius. So this is the second law of Kepler, that these areas are the same, as long as the times you take are the same. So that is the second law. The third law of Kepler took him a little bit of time to come up with. It has to do with the orbital time, how long it takes to go one full cycle. For the case of the Earth, it's 1 year, 365 days. For other planets, it depends on how far they are from the sun. The closer they are, the shorter time it takes for them to go around the sun. Like, for example, Mercury and Venus. The further they are, like Mars, Jupiter, and Saturn, the longer it takes to go around the sun. As a matter of fact, that depends on the distance A. He came up with this relationship that is the square of the period expressed in years. So P is in years, not in other units. It's not in seconds or days, or doesn't matter what other units. It has to be in years, and A in astronomical units, basically 1 AU for the case of the Earth, which is 150 million kilometers. So the distance is not expressed in kilometers, not expressed in miles, not expressed in centimeters, it's not expressed in meters, but rather in AUs. That ratio is constant. So this is basically, in a nutshell, what the three laws of Kepler are. We will have activities related to that. Mr. Galileo came in later on, and he reiterated these laws by doing some observations. For one thing, for example, one of the arguments that was made against the fact that why the planets are not going through the sun in circular paths, because circles are perfect, heavens are perfect, Earth is not, because of men sinning on it. Well, he looked at the moon using a toy at that time that he converted into an observational tool for himself, namely the telescope. And he saw that the moon is not really that perfect too. It has mountains, it has hills, it has valleys, it has all kinds of things. So, in other words, that observation, that argument about the Earth being perfect, not perfect and everything else is perfect, is not correct. Actually, it was the fact that he discovered the 4 moons of the 4 moons of Jupiter. The first night he saw the 3 moons, namely Ganymede, Callisto, and Europa. The next night, actually, he saw also Io. Io is very close from Jupiter, so it takes a very short period of time to go once around Jupiter. The point being in here is, here are 4 objects that revolve around something other than Earth. So the geocentric model is no longer correct. Not everything revolves around the Earth. Here is a very good point to that effect. Okay, that's one thing. The other thing, also he observed the rings of Saturn. That too has indications that things revolve other than the Earth. So the geocentric model has been dismantled completely, and now we're into the heliocentric model. And the last thing also is that Venus goes through phases, and those phases, of course, has to do with the sun. So again, and how it revolves around the sun. So again, those are things that basically supported the new heliocentric model, laws that govern it, and we're going to do applications on this laws. Thank you.